Hello, physicists, and welcome. In this session, we'll be looking at collisions where the objects separate after they collide. Let's get started. This is an example of number 2 in the conservation momentum and collision packet. An SUV with a mass of 500 kilograms and a velocity of 50 meters per second, I'm calling to the right the positive direction, is heading straight for a sports car, mass 300 kilograms with a velocity of minus 20 meters per second. Meaning it's moving to the left. The vehicles collide and separate, with the SUV traveling at 14 meters per second immediately after the crash. So there's several things that we're looking at. Calculate the momentum of the SUV and sports car, watch the signs, and the total momentum just before the collision. Calculate the momentum of the SUV just after the crash. Calculate the momentum of the sports car just after the collision. Calculate the change in momentum of the sports car from before to after the collision. And if the crash lasts 0.15 seconds, calculate the force of the crash on the sports car. Hey, so I'm going to roll this into just looking at our last item here. So I'm going to find the force on the sports car. You'll see that the other calculations come out of that. Hey, what am I given? I'm given the mass of the SUV of 500 kilograms. The initial velocity of the SUV is 50 meters per second, positive to the right. We're given the mass of the sports car, 300 kilograms, and the velocity of the sports car initial, minus 20 meters per second. We also know that this is an elastic collision because the objects in the problem separate. We're given the time of the collision, 0.15 seconds, and we know that the final velocity of the SUV is 14 meters per second to the right. Let's take a look at what happens. Our car and SUV collide. Afterward, they separate, both moving to the right. Let's take a look at the relationships we have here. Hey, we know that the force on the sports car, what we're looking for, can be expressed as our impulse divided by time, which is our change of momentum divided by our time as well. We're talking about a collision, so the initial momentum is equal to the final momentum, just the momentum we transferred between the objects involved in our collision. Hey, we could do it this way. Our initial momentum is equal to the momentum of each of the individual items before the collision, and our final momentum likewise is the final momentum of each of the objects in the collision. But there might be an easier way of solving this problem. Because it is a collision, we know that the momentum lost by the SUV is the momentum gained by the sports car. That'll come in handy because we're looking at a change of momentum of the sports car divided by time to give us our force. Let's go ahead and solve it. Hey, the initial momentum of our SUV, that's one of the things we're being asked for, is the mass of the SUV times the velocity of the SUV, so 25,000 kilogram meters per second. Likewise, we can figure out the initial momentum of the sports car is its mass times its velocity. Remember, the velocity is negative, so we have minus 6,000 kilogram meters per second. Remember, momentum has a direction, so if we're going to the left, we have a negative momentum. Hey, let's take a look at our total momentum. We'll add our 25,000 plus our negative 6,000 kilogram meters per second. We have 19,000 kilogram meters per second as our initial momentum, which is also going to be our final momentum. Let's take a look at the final momentum of our SUV. 500 kilograms times 14 meters per second. We see that the final momentum of our SUV is 7,000 kilogram meters per second. So how much did the momentum change? It went from 19,000 to 7,000, so the change in momentum of the SUV was minus 12,000 kilogram meters per second. What does that mean for our sports car? Whatever was lost by the SUV was gained by the sports car. So our sports car gains 12,000 kilogram meters per second. Hey, the force in our sports car is that change of momentum divided by the time. So we have our 12,000 kilogram meters per second, the change of momentum divided by the time, 0.15 seconds, and that equals the force on our sports car, about 80,000 newtons. Give you an idea how much that is. A newton is about 5 newtons in a pound, so that'd be about 16,000 pounds, or about 8 tons of force on the car during the collision. Let's go ahead and give us our sign and put a box around that. Okay, so the plus 8,000 indicates that the change in momentum, that the force is to the right, a positive force. Okay, so for an elastic collision or objects that separate, that's physics for now.